Analog interfacing with ARM Cortex-M4 microcontroller. To interact with the nature, microcontroller use different sensors and actuators. Many of these sensors and actuators use analog interface to connect to the microcontroller. For proper interfacing between these sensors and a microcontroller system, it is required to convert analog signals to digital and vice versa. In order to convert an analog signal into a digital one, we use analog to digital converters. In this video, I will describe the ADC modules available on Cortex-M4 microcontroller available on TM4C series launchpad. So let's get started. So this is the summary that we are going to discuss in this video related to analog interfacing on ARM Cortex-M4 microcontroller. First of all, we will discuss about the ADC modules available on the TM4C123G microcontroller, and after that we will see which GPIO pins can be used for interfacing the ADC module, and we will also see the ADC block diagram and different components of the ADC module, and after that we will see different configuration steps. So let's discuss about the ADC module available on the microcontroller. The TM4C123 microcontroller contains two integrated ADC modules, which share 12 analog inputs and can be operated completely independent of each other. The two modules are successive approximation-based ADC. Each of the ADC module has the following feature: a maximum sampling rate of 1 million samples per second, 12-bit sample resolution, 12 external analog input channels, and one internal temperature sensor. Sampling can be started using one of the multiple triggering sources, and we can also use the channels as single-ended or differential analog inputs. Also, both ADCs have hardware sample averaging capability up to 64 samples. Usually, an ADC in a microcontroller requires processor intervention to handle each conversion. However, sample sequencer-based architecture of TM4C123 microcontroller enables the software to configure up to 4 different sampling sequences with separate custom configuration. The use of sample sequencers in each ADC module makes the sampling of multiple analog input quite flexible and also reduce the processor overhead. The ADC module in TM4C123 has 4 sample sequencers, namely sample sequencer 0, sample sequencer 1, sample sequencer 2, and sample sequencer 3. And any of the 12 analog input channels can be assigned to any of the sample sequencer in any order. Even a single analog input channel can also be used multiple times on a single sample sequencer or a multiple sample sequencers. The 12 analog inputs available on TM4C123 microcontrollers are labeled as ANI0 to ANI11. These analog input channels are multiplexed to these GPIO pins. So when we want to use a specific GPIO pin as an analog input channel, we need to disable its digital functionality that we will see in the configuration steps. So let's see the block diagram of the ADC along with its sample sequencers. This block diagram shows that the ADC module on TM4C123 microcontroller combines 4 sample sequencers with the actual 12-bit successive approximation analog to digital converter. You may notice the sample sequencer 0 allows sampling of maximum 8 analog signals, while the sample sequencer 1 and sample sequencer 2 allows sampling of 4 analog signals, while sample sequencer 3 only allows sampling of 1 analog signal. Also, the sequencer inputs can be configured for any arbitrary analog channels, and it is not necessary to configure all the sequencer input channels. The sequencer outputs are multiplexed to the ADC input and have configurable priorities. In addition, each sequencer can have a separate triggering source that we will see in the configuration step. The ADC block is responsible for sampling rate as well as hardware averaging control. All the analog inputs connected to a specific sequencer will have same sampling rate. It is also important to mention that hardware averaging control is an ADC attribute. Once hardware averaging is enabled, it becomes applicable to all the sequencers which are enabled. The digital output after the conversion is stored to the associated FIFO corresponding to the each sample sequencer. The both ADC modules, ADC0 and ADC1 of the microcontroller, have the same block diagram. Now we will move to the configuration steps of the ADC module. So these are the configuration steps that are required in order to use the ADC module available on the microcontroller. We will discuss these configurations in 5 steps. In the first step, we will discuss the ADC clock gating control configuration. In step 2, we will discuss GPIO configuration for interfacing the analog input for the ADC. In step 3, we will perform some configuration related to the ADC module. And step 4, we'll discuss the configurations related to sample sequencer. In step 5, we will discuss ADC interrupt configuration that will be only required if we enable that settings in the step 4. Let's start these configuration steps by discussing the step 1. As I said earlier, there are two ADC modules integrated in TM4C123 microcontroller. The clock for each ADC module can be configured separately using run mode clock gating control register. This register has this address value. The bit 0 of the register correspond to the ADC0 module and bit 1 correspond to the ADC1 module. Writing 1 to the bit enables and provides clock to the corresponding ADC module. It is very important to note that after clock enabling, we need to provide 3 cycles delay before accessing the other ADC registers. For an example, if we want to enable the clock on ADC module 2, then we need to write this value to the register because it set the second bit of the register. As we discussed earlier that there are 12 analog inputs from ANI 0 to ANI 11 on TM4C123 microcontroller. But these 12 analog inputs are multiplexed to different GPIO pins as we saw in a table. To configure analog functionality on a GPIO pin, the digital function should be disabled by clearing the corresponding bits in the GPIO digital enable register that has an offset value of hex 51C. In addition, the corresponding pin in the GPIO analog mode select register having offset value of hex 528 register should be set to enable the analog functionality on that pin. Of course, we also need to enable the clock on GPIO port by using this register, whether we are using its digital functionality or analog. Here is an example of configuring port B pin 4, which is analog input number 10 as an ADC analog input. For that, we need to clear the bit 4 in GPIO digital enable register and we need to set it in GPIO analog mode select register. And of course, we will enable the clock on GPIO port B. Now let's move to the ADC module configurations. The ADC module configuration involves the following steps: clock source configuration, the sampling rate configuration, sequencer triggering source configuration, sequencer priority configuration, hardware averaging configuration, and control configuration. Let's discuss these one by one. Clock source configuration. In this configuration, ADC clock source is selected. It is done by using the clock source configuration register that has an offset value of hex FC8. If you write the value 0 to its last 4 significant bits, the system clock will be used for the sampling of the analog input channel. But if you write the value 1, then the precision internal oscillator that is running at 16 megahertz will be used as a clock source. The one advantage of using this internal oscillator is that the ADC module can continue to operate in deep sleep mode of the microcontroller. Sampling rate configuration. The sampling rate is one of the most critical parameters associated with an ADC module. We can set the sampling rate by configuring the ADC peripheral configuration register that has an offset value of hex FC4. We can write only these 4 values to this register to get these 4 different sampling rate. Remember, these values are kilo samples per second. The maximum sampling rate that we can have at this ADC module is 1000 kilo samples per second or 1 million samples per second. It is very important to note that when we attempt to configure ADC with sample rate that is not supported by the device, then the ADC either continue with the default or more recently used sample rate. Sequencer triggering source configuration. Each ADC sequencer can be triggered for sampling by different sources, including processor, GPIO pin, timer, PWM, or comparator. The triggering source selection is done by configuring ADC event multiplexer select register that has an offset value of hex 014. Using different triggering sources at different rates for sample sequencer allowed to sample analog inputs at different sampling rates. Once the triggering source is selected, we need to keep in mind that each triggering source has its own register for triggering and starting the sample sequencer. For example, if you select the processor as a triggering source in this register, then you need to write this register offset value hex 28 to start the sampling process. Similarly, if we have configured the PWM as a triggering source, then the sampling can be started by writing to the register that has an offset value of hex 01C. So this slide shows how we can configure the ADC trigger mux register. As you can see, this register has been divided into bit fields of 4 bits, and these are the different values that we can write in order to select the different triggering source. For example, if we write any of the bit fields with the value 0, then the processor will be the triggering source. And if we write value 1 or 2, then the analog comparator 0 and 1 will be the triggering source. Similarly, we can write value 4 in order to use an GPIO pin as a triggering source, and the value 5 makes the timer as the triggering source. If we configure the value 6, 7, 8 or 9, that makes the PWM generator 0, 1, 2 or 3 as the triggering source. And if you don't want to use any of the above triggering source, you can just configure the value hex F that will enable the continuous sampling mode and which does not require any triggering. Sequencer priority configuration. When multiple sequencers are triggered simultaneously, then the order of sampling among the sequencer is decided based on the assigned priority. We can assign the priority to each sequencer by using the ADC sample sequencer priority register that has an offset value of hex 020. Out of reset, sequencer 0 has the highest priority and the sequencer 3 has the lowest priority. When reconfiguring sequence priority, each sequence must have a unique priority for ADC to operate properly. So in this register, as you can see, these bit fields shows the priorities for the different sample sequencers. By default, all the sequencer priority bit fields follow a common definition. Configuring a value of 0 makes the corresponding sequencer highest priority, while a value of 3 corresponds to the lowest priority. Like if we want to make the sample sequencer 3 the highest priority, then we need to assign a value 0 to this bit field. Hardware averaging configuration. Hardware averaging functionality is used for improved resolution, and that can be achieved by configuring the ADC sample averaging control register that has an offset value of hex 030. When hardware averaging is enabled, the ADC performs oversampling to average multiple samples. 3 least significant bits of these registers can be used to write different hardware averaging values. So the value set in this register takes the 2 raised to power that value samples for averaging over. For example, if you set 0, then no hardware averaging is applied, and if you set the value 2, then it will take 16 samples, because 2 raised to power 4 is 16, so it will take 16 samples in order to perform the hardware averaging. Remember, as we discussed earlier, hardware averaging is the feature of the ADC module. When it is enabled, then it will be applicable to all the sample sequencers. ADC control configuration. This configuration step involves 2 steps. The first step is the choice of ADC voltage reference. That is done by using ADC control register having offset value 0 hex 38. If you set the bit 0 of this register, then it will use the voltage supplied at VDD A and ground A as a reference voltage. It is important to note that values set in this register apply to both ADC module. So it means that we cannot set the internal voltage reference for one ADC and the external voltage reference for the other ADC. The second step is the enable or disable each sample sequencer individually. That can be done by using ADC active sample sequencer register that has an offset value hex 000. So this register's bit 0 to 3 corresponds to sample sequencer 0 to sample sequencer 3. If you set a bit to 1, that will enable the corresponding sample sequencer. Also, the bit 16 of this register is read only, and that bit can be read in order to check the status of the ADC. It is busy or not. So this is the summary of the configuration steps that are required for configuring an ADC module. For all these registers, we have their offset values. We can calculate their address by adding these offset values to the base address of the ADC that we will be using. For example, if we use the ADC 0, then the address for the ADC peripheral configuration register will be hex 40038 FC4. Similarly, we can calculate the register addresses for all the other configuration registers. So now let's move on to discuss the configuration steps for a sample sequencer. ADC sample sequencer configurations. Each sample sequencer can be configured independently using its associated set of registers. The set of configuration which can be performed independently for each sample sequencers are described as: the selection of an analog input channel for each sequencer is completely independent and can be performed separately. It is also possible to configure same analog input for multiple channels of the same sequencer. Each sample sequencer analog input can be configured for single-ended or differential type of the input. When using a sequencer, it is not necessary to use all of its channel. Rather, any arbitrary channel of the sequencer can be configured for end of sequence. For instance, any of the channels from 0 to 7 can be configured as end of sequence for sequencer 0. When a sequencer is triggered, sampling is started at the programmed sampling rate and continues until end of sequence has been reached for that sequencer. It is important to note that before modifying the ADC configuration parameters, it is good practice to disable the appropriate sample sequencer. Let's discuss some of the configuration steps for configuring the ADC sample sequencer. Input multiplexing configuration. The analog input channels can be assigned to ADC sequencer by configuring the ADC sample sequencer input multiplexer register. So for each sample sequencer, we have its own ADC sample sequencer input multiplexer register. You can notice the different offset values for these registers. It is important to note that the sample sequencer 0 can be configured for up to 8 analog channels, and sample sequencer 1 and can be configured to 4 analog channels, and sample sequencer 3 can be configured only for 1 channel. As we discussed earlier that there are 12 analog inputs, so we can only configure a value from 0 to 11. This image shows the register configuration for the sample sequencer 0 because it can configure 8 analog input channels. So this register has been divided into bit fields of 4-bit values that can contain a maximum value of 11. For sample sequencer 1 and sample sequencer 2, we will be having only these 4 input mux values, and for the sample sequencer 3, only the input 0 mux value will be available. So each of these bit fields is used to configure an analog input channel for the corresponding sequencer. Configuring a value of 2 to the bit field input 0 mux assigns analog input channel 2 as the first input to the sequencer 0. The possible values that can be configured, as discussed earlier, are 0 to 11, which correspond to the 12 analog input channels. Sequencer control configuration. Each sample sequencer in ADC module has a separate sequencer control configuration register. As you can see, for each sample sequencer we have listed separate control register having different offset values. The only difference is that for sample sequencer 0 we have 8 such configurations, while sample sequencer 1 we have, while sample sequencer 3 we have only 1 such configuration set. Let's discuss the sample sequencer 3 control registers configuration that has a single configuration set. In this configuration set, D0 bit 0 correspond to the sample differential input select. If you set the value of this bit to 1, then the analog input channel will be treated as differential input. The second bit of the configuration set correspond to the end of sequence. If you set the 1, it means that sample will be the end of sequence for that sample sequencer. The third bit is the sample interrupt enable. That is used if you want to generate an interrupt when the sample sequencer has completed its processing. And the fourth bit, which is bit 3, that correspond to the first sample temperature sensor select. When this value is set, it reads the internal temperature sensor during the first sample of the sample sequencer. It is very important to note that when configuring a sample sequencer, the end bit must be set, even if you are using a single channel with any of the sample sequencer. Sample sequencer result. The ADC sample sequencer result FIFO register contains the conversion results for the sample sequencer. We also have the separate registers for the different sample sequencer having different offset values. So these registers will contain 12-bit conversion results from the ADC. The reads of this register return conversion result data in the order sample sequencer 0, 1 and so on until the FIFO is empty. Meaning that the reading these registers can be read sensitive because these registers acts like a FIFO, first in first out memory type. So this table holds the summary of the different registers associated with the sample sequencer's configuration steps as we discussed earlier. So that's all for the sample sequencer configurations. Let's move on to ADC interrupt configurations. Step 5, ADC interrupt configuration. Interrupt configuration for each analog input channel can be performed separately as mentioned in the description of ADC sequencer control configuration register. In addition, each sequencer can be source of interrupt as well, which can be configured using the ADC interrupt configuration register as shown in this table. The least significant 4 bits of these registers are used for interrupt masking using status and clearing of the interrupts for the 4 sequencer. The bit 0 of these registers correspond to the sequencer 0 while bit 3 correspond to the sequencer 3. So that's all related to the analog interfacing available on ARM Cortex-M4 microcontroller. If you have any question, feel free to ask. Thank you. See you next time.